Okay, so I want to point out a couple of things. I'm not sure if you guys remember, but there is a practice problem that was supposedly due today. If Well, I didn't mention it last week. I just mentioned it briefly the first week of class, but you may take additional few days and turn it in, since I didn't mention it last week. So, but pay attention under the week we are in. If there's practice problems that is available, that means it's due the following week that the lecture is given. So, for example, there is one open for this week. This means this is due next week. So now you have two that you can work on. You didn't know that? Okay. So for today's lecture, there are a couple of reading material in addition to the references I've given you in the, let me go back step so that you see here. So here, in addition to book chapter and reading material for topic of the third topic, under, if there are additional readings, I would post them under the specific week. So please make sure that you check them out here. I'll go over all of this in class, but this is just additional detailed information if you want to understand more the method and how it functions. So there are additional information here. And then in addition to that, I've recently created a document that would be helpful for this week. And it is related to protein structure characterization and some examples as to when it's needed or is done, and then the most common tools that are used. So again, I'll talk about most of this in class, but this is just more kind of background information. Okay, so close out of this. This is not the most easy way. All right. So that's that. We can continue where we left off last time. Ugh. Oh, come on. Where is that stupid thing? Okay. Some recap questions so that we can move on. Let's see, what do you remember in terms of what's the role of hydrophobic residues in the folding of a protein? What do you remember about that?
Hydrophobic goes to the middle.
Yeah, so hydrophobic actually go to the center of the protein, hiding from the water. So it's kind of wants to associate with another residue, a hydrophobic residue wants to associate with another residue and hide away from water, so it drives the folding process. So hydrophobic interactions between residues drive the folding process in terms of hiding these residues from water. Okay, and when that happens, the first structure is called secondary structure. So you have your primary structure, which is chain of amino acid, and then the first initial folding that happens is called the secondary structure. And with the hydrophobic interactions going on, what other interactions are promoted within the protein that stabilizes secondary structure? So what gets kicked out, basically? Huh?
Water.
The water gets kicked out, and then with that, hello.
Hello.
the is this usually the time that you guys will be able to make it?
I don't.
What?
This one just ran over because there was a lot of questions.
Okay. Okay. Are you guys okay starting at 2 instead of 1:55? Is that okay with your schedule? Okay. So we'll plan on starting class at 2 next week, and hopefully these guys will catch up. Okay, and then I forgot the sheet of participation. So far we have Jordan participated one time and Sophia. Okay. Ah, yeah. So water gets kicked out, and with water being kicked out, what kind of bonding can now happen between residues within the protein? Hydrogen bonding. Very good. So now we have the hydrophobic interactions driving folding of the protein and kicking water out. Then your secondary structure is stabilized by hydrogen bonding because no more water is no more competing for hydrogen bonding. It's kicked out of the interior moiety. So what about tertiary structure? What kind of forces may stabilize tertiary structure? So you have the secondary structure, but you still have a lot of free energy, then you still have some more folding and rearrangement. What kind of interactions take place to stabilize the tertiary structure? There are dipole, or in other words, we can call them van der Waal. We still have hydrogen and hydrophobic interactions as well. What else? Disulfide linkages. And one more. You have charges, right? Electrostatic or ionic interactions. So all of these interactions take place, and every bond that is formed, it reduces free energy and causes more stability of the molecule until you reach the most stable stage, and thus your structure is more stabilized now. Speaking of free energy, what is enthalpy? Remember? Delta H?
Enthalpy is the energy contained in a bond.
Yes, the enthalpy is the total energy contained in bonds, and any change in that would be change in the contained energy, or delta H. What about entropy?
Degree of randomness.
Degree of randomness. So the chaos, in other words. When you have a lot of free energy, you have a lot of entropy. And when there's a lot of entropy, if you remember, the delta G equation is delta H minus T delta S. Delta S is for entropy. So when you get a negative delta G, that means denaturation is spontaneous, because now you have a lot of chaos and the protein unfolds. Okay, so there are solvents that would disrupt interactions. So what would disrupt hydrogen bonding? What kind of solvent? Do you have any idea? Those of you that ran gels before, what do we add sometimes to the sample? You dissolve it in the buffer. What does that buffer have? A detergent, STS. So detergents can actually disrupt hydrophobic, hydrogen bonding, ionic interactions. Any non-covalent bonds can be disrupted by detergent. Hydrogen bonding specifically can also be disrupted by urea. So urea also for, let's say, running what? I lost it. It will come back to me. But anyway, urea also will disrupt hydrogen bonding. What would disrupt specifically disulfide linkages? Reducing agent. Yes. So we talked about few reducing agents. We said beta-mercaptoethanol is one, DTT is another, cysteine is another, glutathione is another, sulfites is another. How about ionic interactions? So their charges. What can interfere with the charges? What kind of solutions may interfere with the charges? If you change what in the solution, you might cause change in charge. Change the pH, you're changing the charge, so you might cause more repulsion to occur between originally a positive and a negative. If you change the pH to extremely acidic or extremely basic, then you unify the charges and you cause repulsion. Another solution that might cause repulsion or ionic interaction breakage of bonding is a high salt concentration solution. When you have a lot of charges from salt, the salt will shield other charges and thus prevent ionic interaction. Um, how does the free energy concept explain the folding of the protein? We touched upon that a little bit. So you have a lot of free energy, so it is unstable to have so much energy going on, so much chaos. So bonding starts to occur to contain the free energy into bonds. So can contain the chaos into a stable state. So that's that. Any questions about last week's topic? Anything you'd like me to recapture or explain? Okay, so I'd like you to think about questions for next time we come back to lecture next week. So to start conversation at the beginning of the class, think about questions. Let's start discussion at the beginning of class. Okay? And are you sure you don't have anything you thought about for moving on?
I have a question. Sorry, I was not here last week, but the main difference between the secondary and the tertiary structure is the forces that are involved, because, or
Yeah, so the forces are involved, but also it's the additional folding that happens. With the secondary structure, you have initial folding, and on top of that initial folding, more structural folding occur with the tertiary
so the
structure.
secondary is not completely stable.
No, it's not completely stable yet.
So you define the cut line between
That's a good question. How would you define the cut line? There is no cut line usually in nature. In nature, there is not one protein that only has secondary structure. All proteins have some form of structure, because if they're not stable, they want to be stable. Having a lot of chaos is, even when you denature a protein, it will renature into a different form to assume the most stable form. When you don't have a protein with only secondary structure, because it has a lot of free energy that it will not stay. Like if I have a lot of energy, I cannot stand put. I'm just going to be jumping around. So even when a protein denatures, it will assume another stable structure, but it's not the original natural structure. That's why we call it denatured protein. It will always assume a certain stable structure. Yep. That's a good question. Any other questions? Okay. So I think that was the last slide we talked about. Just briefly, we went from primary to secondary to tertiary, and we mentioned that some proteins also, due to let's say high degree of hydrophobic residues or a lot of charges going on, a lot of conjugated groups, they do not stay as a single molecule. They associate. And they associate in terms, and then they form a quaternary structure. So a quaternary structure is an associated molecules of protein. Casein is the most perfect example, where you have 4 different types of caseins associated to form a micelle, which keeps the casein suspended in milk. What keeps it in a micelle is a combination of hydrogen bonding, hydrophobic, electrostatic interactions. So electrostatic is mostly when you have those phosphate groups. You have the calcium pyrophosphate linkages that occur between the phosphorylated proteins. So, and then you have hydrophobic interactions, and the glycated proteins or the glycosylated proteins are negatively charged, and they dominate the surface of the micelle. So you have net negative charge, and that's what stabilizes the quaternary structure in water, due to the high negative charge on the surface of the micelle. So this is one example. Another example is the myoglobin is an association of 4 protein molecules. Another example is not here is soy protein. One of the proteins in soy proteins are usually associated via different types of interactions. And we'll talk about each of those more when we cover different types of proteins. The configuration of the tertiary structure can also be in different types. So you have the fibrous proteins and then the globular proteins. Fibrous proteins, rod shaped, they're mostly high in polar amino acids, because when you have a lot of polar amino acids, then they want to be exposed to water. They don't care. So there's not a lot of interior moiety like a globular protein. When you have a globular structure, that means there are a lot of hydrophobic groups that want to associate and hide from water. So usually fibrous proteins are structural proteins, so such as the collagen, which is a protein that is structural, gives structure. Globular proteins are more of the functional proteins. So enzymes, for example, are globular. Most enzymes, if not all enzymes, are globular. Some food proteins are globular proteins, like whey protein is globular, soy protein is globular. So there are storage proteins. So storage proteins is not on the slide, but storage proteins in a plant usually are globular proteins. But also we have globular protein in dairy, such as whey protein is a globular protein as well. Alright, so the composition of a protein, when you hear a homoprotein, that means it's only made up of amino acids. So it's your typical protein is made up of only amino acids, such as beta-lactoglobulin is a homoprotein. It doesn't have any other groups. Phosphoproteins, you have phosphate groups associated with it, such as alpha and beta casein. You have glycoproteins, where you have glycosylated units. And these both phosphorylation and glycosylation of the protein occurs post-translational in the cell. So example of that, kappa casein is a type of protein in milk. Also beta-conglycin, a type of protein in soy, is also glycosylated protein. Both, all of these alpha, beta, and kappa may play a major role in the stability of the casein micelle. Like I said, the phosphorylated protein form calcium bridges within the micelle, and the glycosylated protein are mostly on the surface, providing stability to the micelle due to charge. Okay, so another one is a lipoprotein, which is also has a lipid or a lipid portion conjugated to the protein, such as egg yolk proteins, which makes them excellent emulsifiers. And we'll talk more about that later when we talk about functionality. So another characteristics of a protein itself is its net charge. So all of these amino acid residues, they carry different functional groups, but some are positively charged at neutral pH and some are negatively charged. So the positive cancels the negative, and at some point you end up with a net charge. So it's either going to be in a positive charge or in a negative charge due to the composition of the protein. So so when you have a net charge, you're not at the pH of the isoelectric point where you have equal negative and equal positive. There is no charge. But when you have a net charge, whether it's positive or negative, that's an indication of solubility. That means it's an indication that the protein has enough charges to interact with water and repel another molecule of a net negative charge or a net negative charge or a net positive charge. So when you have molecules that are all positively charged or have net positive charge, they will repel each other. If you have molecules in solution that are net negative charge, they will repel each other, interact with water, and be soluble. So what happens if we change the pH? So at the isoelectric point, that means you have equal pluses and equal minuses. But as you titrate with the base, you're adding OH minuses. Some of your positively charged groups, some of the amine groups are going to donate a proton. Say, okay, It's too basic around here, take my proton. By doing so, you will end up having more net negative charge because of the carboxyl groups that are there. So an amine group goes from NH3 plus, the primary amine, goes from NH3 plus to NH2. What am I doing? NH3 plus to NH2. So it donated a proton and it lost a positive charge. But if you're here and you're titrating with an acid, there are a lot of H pluses in the system. So what's going to happen? The H pluses are going to protonate carboxyl groups. So you go from COO minus, you go to COOH. So you lost a negative charge, and your amine groups remain positively charged, so you end up with a net positive. Okay? So titrate with an acid below the isoelectric point, you have a net positive charge. Titrate with a base above the isoelectric point, you end up with negative charge. What happens when you add salt? Claire knows this. What happens? Hi. What happens when we add salt to the protein? It comes out of solution. Why? Because the salts, well, sometimes you do salting in and sometimes it's salting out, and we'll talk about that in another lecture. But a lot of salt, let's assume a lot of salt. A lot of salt, what's going to happen is going to shield the charges. So let's say ammonium sulfate, the ammonia with the plus is going to shield the negative, and the sulfate with the negative is going to shield the positive, and the protein is no longer interacting with water, no longer repelling each other, so they will precipitate. Okay. At close to neutral pH, what would be the net charge of a polypeptide that has 5 residues of lysine, 4 residues of arginine, 6 residues of aspartic acid, and 7 residues of glutamic acid, and 11 residues of glycine? Okay, so think about it in a simple term. There's actually a chemical equation that you would derive the charge when you know the composition, but we're not going to go there. But think about what would be the charges of lysine, arginine, aspartic acid, glutamic, and glycine at neutral pH. And from there, derive the net charge of that polypeptide. So, do you remember lysine? Does it carry a positive charge or a negative charge? Is it a basic or acidic amino acid? It's a basic. So lysine and arginine are basic amino acids, so the R group has an additional amine group that is positively charged. So at close to neutral pH, these two will carry positive charge. What about aspartic acid and glutamic acid? Acid. So they carry carboxyl groups in their R chain. Therefore, they're acidic, so they are negatively charged close to neutral pH. So you have 9 residues that are positively charged, 13 residues that are negatively charged. What about glycine? Neutral. Glycine is your smallest amino acid that the R chain is only hydrogen. So it doesn't carry a charge at neutral pH. So just doing simple math, very simple, you will come up with a net charge of -4. But again, there is a chemical equation that you would derive a charge of a protein based on composition. But this is just to drive the point of fact that every protein or peptide has a net negative charge based on the composition. Okay? Questions? All right. So that concludes the second last week's lecture. And we're going to move on to today's lecture. Okay, so this lecture combines my love and passion to analysis and proteins. Food analysis and proteins. My favorite lecture. Okay, so protein analysis encompasses not only analysis for quantification, obviously, but also characterization and separation and identification. So it encompasses different types of analyses. Knowledge stack. In this lecture, some of you that has taken food analysis will have some review. Others might be new information, so I'm going to refer you to the chapters. I already put references for you. I won't be going into detail in certain aspects because these are stuff that you've taken before, I'm sure, as an undergraduate. If not with me, with another professor in food analysis. So, knowledge check. Which of these can be used to separate or isolate proteins? Take a wild guess. You're familiar with chromatography, right? All of you? Okay. Size exclusion chromatography is based on separation of proteins based on size, separation based on charge, and anion is based on negative charge, and affinity chromatography is separation that is very specific, where interactions between stationary phase and your molecule is very specific. So all of these chromatography techniques, in fact, can be used to separate and isolate proteins. Okay, the following analytical techniques can be used for structural elucidation. What do we mean by structural elucidation? That means deducing the structure of the protein, or getting information on the structure of the protein, whether it be its composition, whether it's molecular configuration, whether it's molecular weight. So, by process of elimination, A and C. Any other answers? Nobody's gonna bravely guess? Huh? All of the above? You ruined it. No, it's only A. So ELISA has nothing to do with determining the structure of your protein. ELISA is an identification kit or tool where you identify the presence, and sometimes you can quantify a unique protein. Western blot is also another form of immunoassay where you qualitatively identify the presence of a particular protein, but based on interaction with an antibody. So your protein as an antigen will react with antibody, and you will visually see the interaction, but they give you nothing about the actual structure of the protein. So N-terminal sequencing is a methodology that I'll talk briefly about today, where you actually determine the composition or the sequence of amino acids starting from the N-terminal amino group. So protein analysis encompasses quantification, separation and purification, and characterization and identification of the protein. By characterization, it's mostly structural characterization, compositional characterization, as well as other physiochemical characteristic characterization. So protein analysis is important when we are developing ingredients or preparing ingredients or protein ingredients. We have to quantify the total protein in the isolate. We obviously follow separation and purification to get that protein ingredient, and we carry out characterization to determine, okay, so what would be the surface charge of that protein? What's the surface hydrophobicity? What's the isoelectric point? What is the polymerization status of that protein? With that, I can tell, if I know the structure of the protein I analyze, I can predict function. So protein analysis is obviously done a lot when you're doing basic research, like what Claire is doing. What are you doing?
Trying to extract protein.
She's trying to extract protein from camelina to determine if these proteins are going to be functional proteins. So she does protein separation, quantification, and she's going to do characterization. Industrial application, we're going to spend some time giving you examples about that. But so this is kind of an overview. And when you're doing or carrying out protein analysis, you keep in mind legal, nutritional, safety, economical, and functional implications. Can you give me an example where legal matters, nutritional, safety, economical, function? You can pick any and give me an example.
Melamine, milk.
Melamine in milk. How is that related to protein?
Well, the issue is that it, I was thinking of it more that the issue is that it gets quantified as protein.
Ah, yes, okay, yes. So yeah, quantification of protein by following nitrogen analysis might cover up if there is an adulteration with a substance that's high in nitrogen. Okay, something else.
With like high protein foods, the legal aspect would come in to make sure that manufacturers are actually hitting the requirements they're claiming to make their
Exactly.
health claim.
Whatever is they are claiming on the label is actually present in the food. So if they're claiming high protein beverage, what's the minimum amount of protein in a beverage to be able to claim as high protein is about 4.2% protein. So if you have a 4.2% protein in your beverage, you can claim a high protein beverage. Nutritional. So we talked about you want to make sure whatever protein you're isolating, if it's a new source, you want to make sure that you know what's the essential amino acid composition, what's the digestibility of this protein. You need to know these things so that you can determine the quality of that protein that you will eventually formulate with. Safety, you want to make sure that you don't have allergens that you are not declaring on the label. So that's one. Another safety is if you have toxins. Some proteins can be toxic. So if they're present, you need to make sure either you inactivate them or remove them from the system. Economical, it's always important. I think we deal with that a lot. So what's the yield, right? So if you're extracting protein, how efficiently you're extracting protein? Are you getting all the proteins out from your system, or you're throwing away proteins that you can extract? That is one thing. Another economical example would be, are you following an industry feasible approach with minimal cost to produce a product? That's another example. Functional implication. Whatever you do, whether it's processing or modification or formulation or whatever, how is that affecting structure of the protein? And if the structure is affected, the function is affected as well. So it's a huge, huge topic, and I have tons of examples for you. It could be a semester worth topic, but I'll try to not enjoy myself a lot and talk more than I should. Okay. What's the importance of measuring protein content? Before I go into that, these are your standard methods, or typical methods, I should say, for analyzing protein content. So you have the famous Kaldal and Dumas. They're both official methods, and they're both made based on determining nitrogen and converting to protein. So Infrared spectroscopy is a method used for online monitoring of protein content. So it's a quick, non-official method, a secondary method of analysis, and you have a handful of research methods that mostly work with clear solutions of proteins for research purposes. So if you're isolating protein and then you're fractionating it with HPLC, let's say, and taking fractions, and you want to know how much protein you have in that fraction, if it's a pure fraction and clear, you can do any of these research methods. But before giving you a summary, more explanation about these methods, why is it important to measure protein content? Can you give examples where we have to measure protein content?
Nutritional level.
Nutrition labeling, yeah. What else? Yes, sir.
Like cost.
Cost.
So price points.
Yes, so exactly. So we want to know the protein, for example, protein is expensive. Wheat flour has a premium based on their protein content. So, yeah, for cost, what else?
The CFR of a specific food product.
Yes, so there is a minimum requirement for, what do you call it, standard of identity. Yes, what else? Think a little bit outside the box.
Collecting for protein when you're analyzing fiber.
Oh, okay, yes. Correcting for protein, actually, and I thought you were gonna say when you are determining functionality.
That too.
Yeah. For example, if you want to determine a certain function, like let's say emulsification, you want to determine how many grams of, or how many milliliter of oil 1 gram of protein emulsifies. So you want to know in your powder how much protein you have so that you can do the math later on and determine the functionality based on the protein in your sample rather than the powder. Okay, what else? And of course, correct for fiber determination. If you know how to determine dietary fiber, you might know what Claire is talking about. If not, don't bother. That's one lecture long, if I want to talk about dietary fiber. What else? Okay, let me reveal. So you talked about nutritional labeling, you gave examples about CFR and cost that are not there, but they were all valuable information. A protein fractionation and purification, we talked about that. When you isolate the protein, you want to determine how much protein is in your final product and determine your yield. Again, yield is important for cost purposes. Functional property, we talked about that. Biological activities, for example, if you have an enzyme and you want to determine the activity of the enzyme, so you want to determine that based on gram of protein, because enzymes are protein. So you determine the unit of activity per gram of that enzyme. Okay. So here's the summary table, which I summarized the principle and what each method measures, the sensitivity problems, and whether or not it's destructive, meaning once you use up the sample for the analysis, you cannot use it for anything else. So this is a review for you. Some of you already know this, others you might want to go back to the references, but basically, just briefly, Kaldor and nitrogen combustion method are based on measuring nitrogen. One is chemical, one is instrumental method. And measuring absorbance at 280, you have those tyrosine, tryptophan, and phenylalanine as well. They absorb light, and every protein has them. So that you can measure protein content of a clear solution using UV absorption. You can measure peptide. If you have hydrolysate, you won't necessarily have in the hydrolysate or the peptides, they might not all have these amino acids, so they might not absorb light at 280. Then you want to measure absorption of the peptide bond for light. And that's actually an average, but it can go from 208 to 210 to 220 is the general wavelength for measuring absorption by peptides. All of these other methods are chemical based. You react on either with for example, a dye, or here based on the reducing power of the peptide and other amino acids, and so on. OPA, you'll hear that, hear me repeat that quite a bit for different purposes, but it's a reagent that reacts with a primary amine and gives you a fluorescence, and you measure that. And ELISA, I will talk about it also a little bit briefly today, where the protein reacts with an antibody and there is a labeling with enzyme, and the enzyme converts the substrate to a product, and you get a colored product that you would measure absorbance, and you can construct a standard curve and determine concentration. So again, I provide you references for these methods. Either you just look at this and know the summary, or if you want more information, you can go to the references. Okay, so why do we want to separate proteins? Can you give example in certain cases that we want to isolate proteins?
To, if the fractions have specific functionalities.
Yes.
To enhance that.
Yes, so you want to isolate proteins, probably take a complex protein mixture and then fractionate it into different components, and then look at the functionality or bioactivity of each component separately. Good. But if you have a food matrix, why would you want to isolate the protein out of that? To generate, to produce isolates or concentrates, ingredients. So protein ingredients are used in so many different applications. So protein separation and isolation is important in industry for production of protein ingredients. Let's see, there are others. So we purify proteins for further analyses. Like Sonia said, we can fractionate, look at different fractions, different functionality of each fraction. Also, we can isolate proteins that act as substrates. For example, casein is often isolated and used in enzymatic assays to determine enzyme activity. So sometimes you isolate to produce substrate, or you isolate to get purified enzyme, because enzyme is a protein as well. So you can use them in analytical assays. And you isolate to understand more about the structure of the protein, the chemistry of that protein, its functionality, its bioactivity, from a basic research perspective. So I just want to mention that today between 9 and up till 1:30, I probably changed the lecture like 100 times, and I kept uploading versions. Final version I uploaded before I came to class is the most updated version. So if you have printed out some version, the latest one was uploaded just before I came to class. There's just few modifications and few additions, but I kept adding stuff. Could not resist. Okay, so if we're focusing now on protein separation and purification, in order to separate the protein, we need to know a little bit about the characteristic of that protein. So we already know that proteins differ in nutrition quality and differ in functional properties, but for separation purposes, we want to know more about the biochemical characteristics. Because the biochemical characteristics of the protein, and if we know a little bit about that, we can devise a protocol to isolate that protein. So some of the biochemical characteristics that are helpful when we are selecting methods of separation is, what do we know about the protein solubility? Is it soluble more in alkaline conditions? Is it soluble more in a little bit of a salt solution? What do we know about that protein solubility? Other important is biochemical characteristic, it's thermal stability. So if I'm after just precipitating out the protein and just using it as an additive, and I don't care whether or not it's going to be soluble or whether or not it's going to be a good emulsifier. Just I want mixture of protein to add an increased amount of protein in my product, then I might induce thermal precipitation, meaning I heat up the protein to high concentration and just precipitate it out of solution. But I need to know at which temperature that happens. Different protein precipitate at different temperatures. Size. If I know the protein size, I can select a particular membrane with a particular cutoff so that I can isolate it from the different components of the sample. Charge. What's the net charge? That will impact what pH and salt concentration, for example, I could use to isolate. Adsorption characteristics, that would help me if I want to use affinity chromatography. What would that protein interact the most with? And biological affinities, do we know? What do we know? If it's an enzyme, what enzyme inhibitors are present that I can use them as ligand on affinity chromatography? So all of this information is helpful and will lead us to identify a procedure for separation. And all of these are dependent or are impacted by the composition and molecular structure of the protein. So for example, whey protein is a globular protein, casein protein is an open structure protein. So I know from a globular protein has less thermal stability than an open structure protein. So this might precipitate then at a lower temperature than casein would. And then if I look up literature more, I would know exactly the temperature that this will precipitate versus an open structure protein. Talk more about that. Another example, which might be different if you printed your slides earlier. This example here, I put it's a kind of animation of the structure of soy protein, which is a quaternary structure protein. See these red lines here? These are indication of disulfide linkages. And so it is, and there are dotted lines due to hydrophobic and hydrogen bonding interactions. So this is a very complex kind of quaternary structure, and isolating it and fractionating it depends on how can I, if I want to isolate certain units, maybe I should break disulfide linkages. If I want to isolate them completely, I should not only break disulfide, I need to break hydrogen and hydrophobic bonding. So if I know the composition and the molecular structure, I might have an idea how to approach isolation and separation. Okay. Questions? All right, so what are some special considerations for protein separation and purification? So what do I need to keep in mind when I'm devising a method for separation? Or not just keep in mind, to consider and to devise my procedure according to these considerations. Huh? Type of the protein, yep. But, okay, yeah, I need to know the type of the protein, but
Can you denature it, or do you need to have it maintain functionality at the end?
right, exactly, definitely. So what do I want in an ultimate application for that separation? Do I want to maintain the functionality of the protein? Then I have to be really careful in the choice of the steps I follow for isolation. Good one. What else? How pure I want the sample to be. Do I want to produce a concentrate, which is usually anywhere between 35 to 80% protein, or do I want to produce an isolate, a highly purified protein above 90% purity of protein? That will dictate the type of separation that I want to follow and the level of separation, how many steps are there. One important thing, though, before any of this is the matrix of the food. So if I'm starting with soy protein, for example, soy beans, I want to extract proteins from soybeans. What's other than protein? What is high in soybeans? What component, nutrient is high in soybeans? Oil, fat, lipid. So I need to remove lipid first. So depending on the matrix that I have, I would start with, okay, I need to remove fat first before doing anything else. That's just an example. So, so we talked about the first three. The last one also we touched upon a little bit, cost. So how expensive is the procedure going to be? Okay, am I going to use chromatography? It might be more expensive than using membrane technology to isolate my protein. So also, what starting material do I have to use to get to the isolate? And can I use a low-cost starting material? Or how much is the yield, for example, going to be? Is it going to be cost-effective? So this is all consideration for preparing ingredients on a large scale or industry scale. To monitor effectiveness of the isolation of protein, what do I measure or determine? If I want to know how effective I was in this isolation, what's the first thing I would do? I'm isolating protein. Measure protein content. Did I isolate the protein, and how much is the final protein in my product? What else? Mass balance determine yield. So it's very important to determine how much of my protein in the original matrix I was able to isolate and collect. What else? Structure, yes. So if I'm isolating an ingredient to be used for functionality, I want to determine what did I do to it? Did I denature it? Did I break it up? Did I polymerize it? Is it at all going to be functional? So you measure total quantity, you determine yield, you assess structure and function or activity. And if I don't know if it's an unknown protein or a protein that nobody has isolated before I did, then I need to determine more about its composition, amino acid sequence, looking at the secondary and tertiary structure, and get all of that information. Okay, here's another summary table have generated based on references. So this is the main information you need to know, but any additional information, background information, you refer to these references. So you go to the document that is labeled protein separation and purification. You'll find references for this information. So one of the first steps you want to do after you remove, let's say, any interfering substances like fat, you will defat it. The next is you want to solubilize that protein out of the other components. So you want to get it out, extract it. So you partition it out. You partition it by using partitioning different liquids, solubility in different solvents. So some proteins like to be soluble in high pH concentration. Other proteins are more soluble at neutral pHs or close to basic. Other proteins, neither. They want to have some salt in there to solubilize. So you want to determine what would be your most efficient extraction method that is based on solubilizing the protein out of the matrix or extracting it out. That would be your first step. Next, you solubilize that protein, but you might have solubilized other components. So if you have, let's say, if you solubilized at pH 8, you might have some sugars still soluble in there, or oligosaccharides. You don't want that. You want to purify the protein. So you say, okay, I need to do additional purification, and by doing that, you could potentially precipitate the protein and leave everything else soluble and get rid of the soluble material. So you can precipitate by high salt, you can precipitate by isoelectric point, you can precipitate by heating, so you can do whatever you want, or even ultracentrifugation. Um, I thought of you when I was looking at it. What's the G that you use?
I was at 85,000.
Oh, close. So instead of solubilizing, you're precipitating. Okay, good to know. We can discuss later. But anyway, so you want, once you solubilize a protein, basically you want to get it out or separate it from other soluble components. So another approach would be membrane filtration. So you will have a membrane with certain cutoff point, that means it has pores, different sizes. Then you will run your solution through it, and it will separate whatever is in the solution based on size. So it's kind of a concentration as well as separation step. You apply pressure while doing that to make it more efficient. Another form of separation after your first extraction is chromatography. And in fact, there are companies that generate or produce whey protein isolate via ion exchange chromatography. Others use membrane technology. So again, I updated this, I don't know which version you have, but mostly the chromatography that can be used is size exclusion, ion exchange, reverse phase, hydrophobic interaction chromatography, and affinity chromatography. But for example, whey protein ingredient most commonly used or prepared is by ion exchange chromatography. So, focusing on the extraction bit, which is solubilizing your protein first, or in this case, precipitating it after you solubilized it. So, let's assume you solubilized it using a little bit of salt, salting in, and then now you have a solution with the protein and other stuff in it, and you want to get it out, you precipitate it at high salt concentration. So what happens is when you have your protein, let's say this is an example of a protein, this purple dot here and purple dot here has a not positive charge, okay? So your protein on the surface has a net positive charge. So it's interacting with water, it's enjoying its environment, it's soluble, and it's soluble with other components as well, like say sugars are still soluble as well. You don't want that, you want to remove them. So you add ammonium sulfate at a particular concentration. The ammonium sulfate, in this case the sulfate, is going to shield, hide the positive charges, and they're no longer interacting with the water, they precipitate and aggregate. So the salt is shielding the charge and as well as competing for water interaction, because your charge groups in the salt will interact with water, taking away the water from the protein. Let's look at this example. If you have 5 proteins in your mixture and you want to isolate protein C in the middle, and from A to E you have increasing net charge. So A is the least charged and E is the most charged. How do I get C out? What do I do?
You could use chromatography.
If I just want to use the salting out, I mean, you can do chromatography, yes, you can do ion exchange, that's true. But if I just want to use the salt principle, any idea?
You could use salt to precipitate everything to a point and then like back it off again.
You are on the right track. So you add salt concentration at a particular concentration that you would find empirically by trying multiple times or by reading references because you know these proteins. Then you will add just enough concentration that will precipitate A and B. Okay? Because A and B are the least charged, so the concentration of salt that will precipitate them will be less than the concentration of salt needed to precipitate the others, because they have less charge. So you start with an X concentration of ammonium sulfate, and A and B will be precipitated. So you can centrifuge, A and B will be precipitated, and C, D, and E will be in the supernatant. You take that, then increase the salt concentration a little bit more, then you precipitate C and you get rid of D and E, or it stays in the supernatant. In this case, you want to take the precipitate and discard the supernatant. Of course, this is a very simplified version of real life. I'll show you a real life example and you're going to go dizzy, but you really need to know a lot about the proteins in order to know, okay, what concentration I want to start with. What salt? Even the type of salt will be different for different purposes. Isoelectric precipitations. Let's say I extracted the protein at pH 8 or 8.5. It's soluble, it's loving its environment, but it's mixed with oligosaccharides. I don't want the oligosaccharides. Okay, I can precipitate the protein if I know its isoelectric point. Alright, I know the isoelectric point of beta-casein. It is 4.6. And I know at neutral pH it has a net charge of negative 11. So it's loving the water, it's interacting with water at pH 7, it's soluble, it's not necessarily clear, but it's soluble. And then I bring the pH down to 4.6, I lose my net negative charge, becomes not zero charge, no longer interacting with water, then you have no more repulsion, you will have attraction via hydrophobic interactions, and then you have aggregation and precipitation. I precipitated my casein out from solution. If I have casein and whey together, whey will remain soluble at pH 4.6. Solvent fractionation. Oftentimes, you can precipitate protein by adding acetone, for example. So in this case, your protein again is interacting with water. You add acetone. Acetone is going to replace water molecules so that your protein is no longer interacting with water, and therefore they're going to precipitate out of solution. Protein denaturation with heat, and this is kind of a not very much used approach unless you don't care about the end use of that protein, because heating is going to denature protein. Sometimes it's going to cause irreversible polymerization, meaning protein molecules are going to interact, forming large polymer, not functional, not useful, hard to digest even. So this is not something that you would do when you care about the final structure of your protein, but still it is used to separate or precipitate the protein. So denature the protein at a particular temperature. Sometimes you denature it even by extreme pH. If you have an extreme pH, you will break ionic interactions and you will cause also opening up of the structure. And then when the structure is opened up, you're exposing hydrophobic groups that were hiding before. You expose them, like now what? I have water in front of me. So I have to hide with another molecule that has exposed hydrophobic groups. So they start liking each other and interacting and precipitating. So here's the temperature of denaturation. So again, the open structure protein versus a globular protein. Globular protein is more prone to structural change. So it will denature at lower temperature. So whey protein denatures at 73. Open structure casein is stable at 140 degrees C for, for quite some time before it denatures. Why? It's globular open structure. And also, um, beta casein doesn't have much of a secondary structure. Secondary structure is mostly random coil. That's another difference between this globular protein that has beta sheet, alpha helix, so it has ordered secondary structure and a globular form, so it's more impacted by heat than open structure. Okay, take 5 minutes. Break.
So when do you want the practice problem set?
Well, I don't really mind since you're graduates. I'm not gonna tie your hands behind your back. Whenever
Okay.
you get it ready,
Okay.
just do that. You just keep it, but you have another one too.
Right.
So,
Don't procrastinate.
yeah, don't, yeah.
Moral of the story.
which questions did you end up submitting?
Oh, I made a tab on the
Oh, okay.
bottom.
I just want to see which ones you picked.
I think I picked all of Brianne's toxicology ones.
Nice.
Almost all of Billy's like weird food service
Yeah.
ones. The flavor one about aldehyde C16.
Oh, yeah.
Most of our bonuses.
Nice. That's good. I'm really
Yeah,
excited
so-
about this shirt.
And I submitted the seven types of FDA dietary fiber as a bonus.
Wow.
Oh, from the new fiber labeling rules?
Yeah. I
What are these 7 different dietary?
beta-glucan,
Mm-hmm.
Wolbus bean gum,
Cellulose.
cellulose, pectin.
Dan, do you want it? I have it in my lit review that's open.
Oh, guava. Yeah.
That was
Quite.
one that was counted.
So the 7 added non-digestible carbohydrates that you can have are beta-glucan, psyllium husk, cellulose, guar gum, pectin, locust bean gum, and hydroxypropylmethylcellulose.
They said non-soluble?
Some are for both.
They're non-digestible.
Non-digestible.
Non-digestible
Oh, okay.
carbohydrates.
Okay.
Hydroxypropylmethylcellulose.
Okay. So here's an example of separation by differential solubility. This is the famous example I always give because it is relatable. So to produce soy concentrate, soy protein concentrate, or soy protein isolate, you start off with a defatted soy flake. So you basically flake the soybeans and then defat them, and then the defatted flakes will be extracted for protein. If you take that route, you do alkaline protein extraction. Usually it's 7.5 is sufficient. So you extract with the pH, with a solution of pH 7.5. And at this point, you solubilize the protein, you precipitate fiber. And also, not only you solubilize protein, you solubilize oligosaccharides and any mono and disaccharides that you might have. And then you do centrifugation, you throw away or discard the precipitate, take the supernatant, and now the supernatant have oligosaccharides, di and mono, and your proteins. So you do an acidification, that means you precipitate the proteins out. At the isoelectric point of soy is about 4.5. So you acidify to 4.5, and then you centrifuge, you take the supernatant. So you wash, you do several washes of that, precipitate, you discard the supernatant in that case, take the precipitate, wash it, and neutralize it. You do not want to dry when the protein is at its isoelectric point. If you do that, you are denaturing the protein. So you always bring back to neutral and then dry, and then you end up with a product that's at least 90%, if not more, protein. So that is one route. This other route is when you actually produce soy concentrate. An average is 65, but it can go up to 80% protein. In this case, you do aqueous alcohol or water wash. In this case, you are solubilizing all your oligosaccharides, monodi, any solubles basically. You get rid of that, and the precipitate will have mostly fiber and protein. And then you dry, then you will have more protein because you start off with a soy flour is around 45% protein. Then when you remove some of the solubles out, you're concentrating the protein. And this product often goes through extrusion, and you get the texturized soy protein products that are common as meat replacers. So separation by adsorption chromatography. So adsorption chromatography, you can, under that, it's either an anion exchange. In this case, this is anion exchange. Your proteins have a negative charge, so they're anions. And you have a stationary phase. Again, I'm not going to go through principles of chromatography here. I'm assuming you guys know. So negatively charged proteins are going to interact with your positively charged stationary phase, and depending on their charge density, the more charged they are, they're going to interact more with your stationary phase, and the less charged they are, they're going to elute, and you can separate based on charge. Um, if you are separating just proteins out of different components, then all of the you can adjust the conditions where you don't really have separations between the protein, but you separate the protein from carbohydrate, for example, and by chromatography like that. Okay. So one note here, once your proteins are separated and they're interacting with the column in order to make sure they elute fast, or that means leave the column fast, you change the ionic strength by adding salt, or you change the pH. Depending on the net charge of the protein you are eluting. Yeah?
One question. When you hydrolyze the protein as well, can you use all these techniques afterwards too?
When you hydrolyze the
The
protein,
protein you are breaking.
yeah.
Can you use all these techniques as well afterwards to separate specific components?
No, when you hydrolyze the protein, then you will have different charges, different hydrophobicity of the peptides that are generated, and also you will have charge, hydrophobicity, and size will be different. Then you might want, depending on what do you want to do. Do you want to separate a particular component, one peptide, for example?
You have to know what
You have to know, but then you can never only use one chromatographic technique to separate, to have pure separation. What you would do is at least 2 or 3 dimensional separation. So you separate based on size, and then you separate based on charge,
so you can characterize everything that it's.
and then you do reverse phase, for example, and then you will see the purity of each fraction you separate and look at the characteristic and then select whatever you want for your purpose. So it's a series of separation. You can never use one separation to isolate all of your components very well or have good resolution, basically. Okay. Just a quick check of knowledge here. If your protein has a pKa value, let's say of not pK, isoelectric point of 5.5. What would be its charge at pH 7? It's not charge. Huh? Would it be positively charged, negatively charged? No.
The last example had 11, and then you brought it kicked down, and then it came out, so it was negative.
At the isoelectric point of the protein, so you have net zero charge. What happens if you're titrating with base? You're increasing the pH. What happens to the protein? Will it lose protons or gain protons? It loses protons, so the net charge will be negative. Okay, so if I want to elute this from the column, I can decrease the pH. If I decrease the pH, my protein will lose the negative charge, right? Reduce the pH to lower than the isoelectric point. then it will become positively charged, so it will leave the column. Okay. So ion exchange, stationary phase is used for ion exchange is usually polysaccharide based because they will allow for large pores within the stationary phase, which is suitable for large molecules like proteins. So you don't use polystyrene, for example, which is a stationary phase specific for small molecules. So the polysaccharide based stationary phase, usually you derivatize the OH groups of the glucose units with either a weak acid or a weak base. If you derivatize with a weak acid, then your stationary phase is negatively charged. Then it would become an cation exchange. If you derivatize with weak base, then you are having a positively charged stationary phase, then you will separate negatively charged proteins. That would be anion exchanger. Okay. Again, this is a refresher. You can go back to the references to remember your chromatography principles. Affinity chromatography, this is based on isolation that gives you the most purity if you are isolating and you want a very specific protein to be isolated, a very specific enzyme or a specific substrate, then affinity chromatography is the way to go, because then you can use as ligand antibodies, for example. These will be very specific to your protein of interest. Nothing else will interact no matter what, so you will elute, everything will leave the column, not interact, and whatever you have left is your protein of interest. Then you will force it to leave by changing pH or salt. By doing that, you'll change the interaction. So you change the charge. If you change the charge, they no longer interact with your column. Or you will add the same ligand that you have in the stationary phase, you add it to the mobile phase, and then your protein will start interacting with the mobile phase and will leave the column. Okay, let's say you used salting out. There is a step that you have to do after you salt out your protein, because again, you don't want to leave all the salt with your protein when you dry it. If you do that, then you are denaturing the protein, and it's with high salt, it loses its functionality. So oftentimes on a lab scale, you do dialysis. In industry scale, you do something called diafiltration. So it's again membrane filtration, and it's a large scale, you concentrate and you remove the salt. So basically what you do, some of you already know this, have seen this, others might not be familiar with dialysis. Who have not done dialysis before? Have you? No? No? Okay, good. So here I have tubings that have 7,000 Dalton molecular weight cutoff. That means the tube has pores that allow anything less than 7 kilodalton to pass through. Okay. Usually for desalting, it's good. We can use 1 kilodalton, 3.5 kilodalton, these 500 kilodalton, 500 daltons, sorry, to just desalt. You don't have to have large pores like that. Anyway, so if you see this, I'm not going to touch it with my hand, but so it is is this a they call snake skin? Snake skin. Have you ever seen real snake skin? Well, it is very long, so they kind of push as much as they can in there. So you just take a certain amount, you pull a certain amount and cut it, depending on the volume of the sample you need to dialyze. And basically you clamp one end, and you pour your sample, whatever, 50 milliliter, 25 milliliter of sample, and then you clamp the other end. And you put it in a buffer or water container. And what happens basically is osmosis. So what will happen is your salt will leave will from a high concentrated area to a less concentrated area, and then you reach equilibrium. Okay? At equilibrium, you have same concentration of salt inside and outside. At this point, there's still a lot of salt in your sample. You throw away the water or the buffer, and you replace with fresh water or buffer. And again, you leave that 3-4 hours, you get to equilibrium, concentration in, equal concentration out. And you do that 3-4 times, and then overnight, at the end, you will still have some salt solution in, some salt in your sample, but it's very, very minute. You will never get to zero salt because it's always equilibrium between inside and outside. But when you do it repeatedly, you reduce the salt concentration to a very, very minute concentration at the end. So it's often done when we are isolating proteins using salt, or if we are adjusting the pH up and down a lot, you end up with salt. If you're adding HCl and then NaOH and then NaOH and then HCl, then you end up with NaCl eventually. So you want to get that out as well by dialysis. So this is a procedure often used just to remove the salt, and sometimes these membranes are coated with polyethylene glycol to prevent water going into the tube, because if you have a lot of water that goes in as well, because salt comes out, water can go in, what happens, this is will bulge and sometimes will burst, and then your sample will be very, very dilute. So in order to concentrate your sample and prevent excess water going in, you have that polyethylene glycol layer. So separation by size, and on a laboratory scale, it can be done in a small tube. In an industry scale, it will be done in large membrane setup systems, or even if we want to do it on a pilot scale, you can buy a system that's very expensive. How much is that system? The ultrafiltration system?
Oh, it's like 3,000.
Yeah, you can go walk at Cargill if you want to use that such system. Yeah, you can tell them about it if you want. Is it okay?
Don't know that many details on it.
So it's a system, basically, large scale system where you have a membrane and then there should be a pressure applied that allow the sample or particles to go from one side of the membrane to the other side of the membrane. In this example here, what I have is you have the membrane here and you have your pore. The membrane is porous. You put your sample and then you spin it in a centrifuge, and everything less than certain cutoff for that sample will go through, and everything higher will stay on the membrane on the other side. So for example here, has a cutoff of 30 kilodalton. So if I want to separate different types of proteins in my mixture, one is 100 kilodalton, the others are 30, 70, 60, whatever, then I will use a membrane with a particular cutoff to get those different size of proteins separated. So you basically have the membrane, and then you have a pressure that you would apply, either centrifugation or a pressurized system that allows the flow of particles. So the membranes, depending on the size of the pores, they can be considered as membrane, a microfiltration membrane, ultrafiltration, nanofiltration, or reverse osmosis. So that the smaller, so micro is larger obviously, then ultra, then nano, and then reverse osmosis. So here's kind of the size versus molecular weight and what type of particles will be separated by reverse osmosis. And this, so reverse osmosis, you're basically separating ions and salts because they're very, very small. And then nanofiltration, you separate, you retain, I'm just gonna call, there's permeate and retentate. These are the terms that are usually used. Retentates are what are the substances or particles that are retained by the membrane, they don't go through, and permeate are all particles that go through. So nanofiltration, you will retain particles between 100 and 1,000, and then ultrafiltration, you retain particles between 1,000 and 100,000, microfiltration above 100,000 Dalton. So here's a system, a milk system. Let's say you have milk, and your first membrane that your milk is going to be subjected to is microfiltration membrane. Then fat and bacteria will be your retentate, and then protein, lactose, minerals, and water will pass through the microfiltration membrane. And then the next one, if you have ultrafiltration membrane here, then proteins will be your retentate, and then lactose is going to pass through minerals and water. You put nanofiltration, minerals are going through, and your lactose is retained. And then finally, reverse osmosis, water is going to go through, then you are refining, desalting your water, basically. Refining of the water. Here's an example. So let's say you start with, you have the cheese and you separate the whey, you remove the cream, and then you have the whey. You want to get, the whey is high in what? Protein and lactose and salts, basically. So you have your whey. So if you pass the whey through ultrafiltration, you will have retentate and you have permeate. The retentate, remember from here, is your protein. So you will have the protein here, and then your permeate is a waste stream high in lactose, and some proteins actually escape and go through as well. But mostly you have, if you take that retentate, this is your whey protein concentrate. So depending on how many times you pass it through, you can concentrate it even more, and it goes from 34 to 80% protein. If you want to concentrate that more, you take it to microfiltration. In microfiltration, you take this, what happens is your proteins are going to pass. Here you retain, other than proteins, you retain phospholipids. You don't want them. So from here, if you want to concentrate the proteins more, you put microfiltration, you remove everything larger than the protein, and you will have the permeate, in this case, is your protein that you want, and it's more purified, and that's whey protein isolate. Okay? So we can separate proteins as well by size using chromatography. So in this case, size exclusion, or other names for it, gel permeation. If you hear gel permeation, that means size exclusion as well. And so here you're separating purely based on size, and you can select the media. So you can have different stationary phase that have particles with different pore sizes. So you, depending on the range of the proteins you have in there, you select certain particles with certain pore size. So to visualize that a little bit, so you have particles, and then you're packing the column with your particles, but each particle has pores, right? So this is one type of a particle. Sometimes you choose different particles, and they will have larger pore sizes. Okay? So it depends on the size of proteins you're trying to isolate. If there are large proteins, then you want to go with particle size that has larger pores. If you know that your proteins are more towards peptides and polypeptides, you want to choose smaller pore sizes, particles with smaller pore sizes. So basically you choose your stationary phase. You can pack your column or buy a column already packed with the stationary phase particle size that will work best for your sample that you are trying to isolate or separate. So again, very briefly, it's based on separation by size. So the larger molecules will not penetrate as much through the pores. They will go around the pores, and the smaller molecules will take their time and all pores are accessible to these smaller molecules, then they will be delayed. So if you have the column, the smaller ones will stay longer because they are going in and out of the pores, whereas the larger ones are detained, not going in and out, so they migrate faster. So you will have a chromatogram with larger ones coming out first and smaller ones coming out later. Again, if you need more information, background, you go back to references. I'm relying on your knowledge as undergrads taking this already. Okay. Let's see here. Again, I want to remind you, whenever we say protein separation, and if we have a complex of protein mixture and we want to separate them into pure fractions, not one chromatography technique, you have multiple. Or not one separation technique, you have multiple. At least two, and usually it's three. Three different types of separations. So in this example, what would work best? I was gonna guess. F?
A and C.
Do you all agree with Sonia? What?
All of them wrong?
All of them. So, the second one, you can also precipitate using ammonium salt. So at a particular concentration, again, you need to know what concentration to start with. The protein that has a +2 net charge will precipitate faster. So if we know what concentration of ammonium sulfate to use to precipitate just the +2 charge, then you can take that and then you will have Z separated from X and Y. Now you have X and Y in solution, you can get ultrafiltration with a cutoff of, let's say, 40 kilodalton. Then your 30 kilodalton will be your permeate and your retentate will be the 90 kilodalton. So it will work. Now A and C are practically the same. It doesn't matter in chromatography which chromatography mode you start with. You can start first with size exclusion and do cation next, or the opposite. Doesn't matter as long as you have two-dimensional. As you can see here, two proteins may have the same charge, +5, but they are different in molecular weight. So if you separate based on molecular weight first, then you will get the 90 and the 89 co-eluting together because they're very close in molecular weight. They will come out first and the 30 kilodalton will come out next. So you have 30 kilodalton, but then now you have two proteins together that are very close in molecular weight, but they're different in net charge, so I can use cation exchange chromatography and separate them. One is denser in charge than the other. That means it will be retained on the column longer than the other, and therefore you do the separation. But this is, again, a very simple case where you only have 3 proteins, but in real life you might have 15 different types of proteins that you're trying to separate. Proteins or peptides even. is a complicated but real life separation of a protein from milk. This work actually I used to do when I was at Purdue. I worked with enzymes from milk, and we used to isolate inhibitors of a particular enzyme from milk, and this is what it took to isolate an inhibitor from milk. It's a very lengthy procedure, but it has been established by other people, so you can follow it based on so many different trials. So if you start with milk, the first step you want to do is defat. So centrifugation at 4000 G, you have the fat on the top layer, and then you have the somatic cells precipitate on the bottom. So what you need is, you don't want the somatic cell, you don't want the cream, you take whatever is in the middle. And then you do ultracentrifugation, precipitate, you're kidding. Who's telling me that the class ended? What? What happened? I think it got too warm. What?
The person before you probably left it on, because I know that happens.
Oh. So sad. Select the source to start. Okay.
Yeah, that's true. It's green now.
Yeah, it's blinking. It's thinking. It's still blinking here. Anyway, it's 5 more minutes anyway. Okay. So, we know that the inhibitor that we're trying to separate is associated with the casein portion of the milk. So, we don't want the whey, so when we ultracentrifuge, we can throw away the whey and take the casein. And then the casein is resuspended in water and the pH is lowered. When you lower the pH, we are also precipitating some proteins that we don't want. So we throw away the precipitate and we take the supernatant. At this case, we do salting. Here, at this point, we salt. We add ammonium sulfate. We precipitate what we want, because we know that now our protein is precipitated, and we throw away the supernatant. Adjust the pH, remove the salt, prepare a fresh solution, and dialyze again, and then we add salt. In this case, we add a different concentration of salt, and then we get rid of a precipitate and we get the supernatant. The supernatant we dialyze to remove any excess salt, and we have the last supernatant, and that's where my inhibitor is.
Were the earlier dialyzing steps both to remove salt?
Yeah,
Or
so the
one of each
earlier
adjust?
one is to remove the salt, and then you adjust the pH and you apply another desalting step, because once you adjust the pH, you are also adding salt, because you're going from very low pH to neutral. You dialyze again, and then you use a different buffer, dialyze again, and with different acids and stuff, and then you salt again. Yeah. So in order to determine concentrations and what to use, these are just a lot of chemistry and biochemistry goes into that. What you know about the enzyme, what you know about using different reagents, and a lot of trial and error, and luckily I did not develop that. It was already developed. So, I told you I have a lot to cover and I'm halfway through. How many hours do you have? No. We'll wait till next week. Okay. So, we'll continue next week. Oh, I will send you today, hopefully, sometime in the evening, your presentation assignments.